start, because time is pressing. Welcome to the third and final session of the day. I'm Zachary, and I just keeping an eye on things. But we have three speakers. We have Llewellyn Smith from Oxford, who is leading the Royal Society Working Party on long-term energy storage, particularly with Britain in mind. And we have Tom Bransden from National Grid, who is going to be, or from the ESO, I should say, these days, system operator, who is going to be giving their view of the same problem. And finally, we have Iain Staffell, who may yet tell me, or some of us, what he's going to speak about, but something to do with storage, and that's obvious at the time. Okay, I'm Llewellyn Smith is speaking remotely by Zoom, so I'm hoping that he can hear me. I'm hoping.
Yes, I can hear you.
Well, that's good, and likewise, and we can see your screen, obviously. So, Chris, I'm just going to pass it over to you now. Thank you very much.
Okay, so first of all, I'm very sorry that for family reasons I can't be with you in person. By the way, if you stop hearing me for any reason, please shout. So I'm going to talk about the conclusions and the lessons to be drawn from the Royal Society report on large-scale storage, and I'll say something about the status of the report at the end of my talk. By large scale, I don't necessarily mean large stores. We mean stores that can deliver electricity that would meet a reasonable fraction, a significant fraction of demand. So this could be small stores cycled very frequently. I'm going to go about this slightly backwards. I'm going to begin with the conclusions, and then I'll go through the evidence that led us to those conclusions. Many people have been involved in this. If I listed all of them, it would fill more than a slide. I hope I haven't missed the key people, but I may have done, as I realized during the last talk that I'd forgotten to put Keith Bell there, who wrote the part of the report which is about grid stability. Now, we're going to assume that as the electricity supply is decarbonized, wind and solar will provide an increasing percentage. That's expected because of the cheapest form of generation, and I think what our findings bear out that that's a very reasonable assumption. So the major conclusions are that in 2050, Great Britain's electricity demand could be met largely, even wholly, by wind and solar storage, supported by storage at a cost that compares very favorably with that of using the only large-scale low-carbon alternatives. I'll give you the figures of the cost on the next slide. Now, those alternatives are essentially nuclear and natural gas with CCS, but those are expensive. And if you operate them flexibly to complement high levels of wind and solar, they are very expensive. Now, maybe I should say here that we did not look at contributions from interconnectors. And the reason for that is we think it would be rash to design a UK system that relied on interconnectors, because there are wind droughts, periods when it's no wind, very little wind, and often very cold across most of Europe. And if we need to rely on others in those times, they won't have any supply to provide. In addition to that, they are vulnerable, I'm sorry to say, to political interference. I didn't take this particularly seriously until I heard Penny Mordaunt, when she was the Minister for Energy, saying that we should not build more interconnectors because it would put us at the mercy of the French. So if there are people who think like that, it's probably true. Now, a large amount of long-term storage will be needed, and it will best be provided in Great Britain, not necessarily in other countries. I'll say something about other countries at the end. It will best be provided in Great Britain by hydrogen stored in solution mine salt caverns. And Great Britain, as I will show, has a much more than adequate potential, albeit not widely distributed. Now, I'm going to follow an approach that provides an upper bound on the cost. So I'm going to start by describing an extremely detailed study or the parts of that study, of the case of wind and solar energy supported by hydrogen storage only. That's not because I think it's the cheapest solution. On the contrary, I think quite likely that if you add other forms of storage, it gets cheaper. But it provides an upper bound, because if adding other forms of storage put the cost up, you wouldn't do it. And if it puts it down, I've got an upper bound. Of course, you need something also that can respond extremely rapidly in cases of trips, the proverbial cup of tea at the half time in the FA Cup final and so on. But that takes very little energy. But we can't model that, don't have the time resolution to do it. But we have costed it in the costs. Now, so we're going to look at that in detail, and then I'm going to explain that adding other types of store quite probably lowers the cost. Adding baseload, what about that? Nuclear will increase the cost unless nuclear cost is cheaper than currently expected, and/or we've badly underestimated the cost of hydrogen storage, or at least it's at the top of the expected range. Baseload from BECCS, bioenergy with carbon capture and storage, could lower the cost if it attracts a significant carbon credit. It's very expensive, but it's carbon negative, so it may get a carbon credit, but the potential is limited. The other thing I should say is that we've modeled the production of hydrogen just for energy storage. And you ought to model all uses of hydrogen storage together. And there are potentially many such uses for space heating, some in transport, maybe for making steel, though we don't do much in this country, producing process heat in industry, and maybe in making plastics. But we don't know what that demand is going to be, nor do we know its temporal profile, so we can't manage it. But it's likely that in fact, I think it's certain, if you did model it together, it would lower the cost. So in that sense also, we're getting an upper bound. Now, here is the result. This is the benchmark case of wind and solar and hydrogen storage only. This includes the estimates of the cost of providing 15 gigawatts of batteries for grid services. And it's the cost of electricity fed into the grid, not taken out of the grid. And the reason for that is the model of demand that we're using, which was lent to us by AFRI, the consultancy, is for power put into the grid, so it doesn't contain losses. Secondly, I didn't want to get into estimating the increased or cost of the grid. In fact, it's unclear. A lot of investment's going to be needed in the grid between now and 2050, but it's going to convey more energy. So it's possible, actually, that the cost per megawatt hour will go down, but we didn't want to get into that. So by looking at the cost of electricity put into the grid, we are sensitive to the cost of transmitting energy from wind and solar farms to storage, but not to the gross cost of distribution. Now, here are the results of the average cost in pounds per megawatt hour. So first of all, we've got three cases here for different values, the assumed cost of the mix of wind and solar power that we take, which is 80% wind, 20% solar. And these values, the first one here is based on IEA's prediction of European costs in 2040, but with BEIS's predictions for 2040 of UK load factors. And the other two values are BEIS's low and high predictions for 2040 and for 2040. They don't give 2050 predictions. Now, the first thing to note is, of course, there's a huge suppressed zero in this plot, but the difference of going from, say, 35 pounds a megawatt for wind and solar to 45 is bigger than, I haven't said, these dots here are our low, central, and high values for the cost of storage. And the difference between the green and the brown is that the green is for 5% discount rate, the orange is, or the brown is for 10% discount rate. And the first thing to say is that this is most sensitive to the cost of wind and solar. The change, if you go from the low cost here to the high cost, is smaller than the change in going from 35 to 45 pounds. And the reason for that is that at the sort of levels of wind and solar that we're at, where the cost is minimum, actually 85% of the electricity is coming directly from wind and solar, and only 15% is coming from storage. So the cost of the wind and the energy coming from storage is very expensive, but it's diluted by the 85% that is coming from wind and solar. And the actual cost of the storage doesn't matter so much. You can vary it by a lot, as you can see here. Now, again, let me emphasize this is an upper bound. It's quite probable that adding other types of store will bring it down, and modeling other uses of green hydrogen will lower the cost. How does it compare with other low carbon alternatives? Well, if we look at Hinkley, often erroneously quoted as having a strike price as £92 a megawatt hour, that strike price was when it was agreed in 2012, and it's indexed. And the last time it was indexed in December, it was £114. Inflation's very high, it's going to be higher in the future. And then we have Drax with biomass, £126. So we're certainly beating that if these estimates are right. What about nuclear? The last time Bayes gave an estimate of nuclear costs, they lay in this range here with 90% load factor. That's higher than has ever been achieved in the UK. So that's operated inflexibly. If you operated it flexibly to complement wind and solar, it would go up, of course. What about gas with CCS? This is Bayes' estimate with a gas cost of £24 per megawatt hour, which contributes about £50 to the total. Of course, that again is with an extremely high load factor. If I start varying it to complement wind and solar, it will get bigger. And of course, and then what about the current price? So if we look at the cost paid to generators, which you have to untangle from the wholesale price because there are transmission charges and so on, it averaged in the last decade about £45 a megawatt hour. In the last year, it's been up above 100, of course, because costs have been extremely high. So the fact is that it looks as if this is right. If we went to such a system, we'd be paying more than we were in the last decade, but who said decarbonisation would be cheap, but less than you might possibly have feared. Now, let's get to the modelling. So first, let's begin with the issue. And the issue, of course, is the variability of wind and solar in both the short and the long term. So up here, this is 1992, the wind and solar are 1992, and I'll tell you where it comes from on the next slide. And the demand is AFRY's model of 570 terawatt hours a year in 2050. So you can see the AFRY model in January is higher than in July, of course. You can see dips at the weekend. It's not constant, in fact, because they based it on the weather in 2018. And that's one of the problems. We have wind and weather data for 737 years, but we have not gone back and adjusted for the temperature in each of those years. So that's just too complicated, but I'll come to the effect of that. So you see here in the short term, the problem is a bit of solar in the winter, terrific variability in the wind. In the summer, the solar more important, but varying every day, but also this, on a scale of a week or so, variation in the wind. If we look at the difference between supply and demand, here it is. So this bit below the axis, if we wanted to provide that with, say, gas plus CCS or some other source, it would have to generate with this extremely lumpy profile. It would have to generate exactly the amount needed to fill in the negative bit of that orange curve. If we want to do it with storage, we've got to store the surpluses and put them into the deficits. So you can see what that would involve. But in fact, that would only be the case here with 100% efficient storage. Storage is not 100% efficient. So with storage, if we're going to rely entirely on storage, we'd have to push up the level of supply until the surpluses were bigger than the deficits they have to fill by 1 over the round trip efficiency. Now that's the short term. What happens in the long term? So we've looked at 37 years of data, but I've plotted here 36 years, because if you look at a year it's best to look at a year from April to March. And the reason for that is if you look at a calendar year, you're mixing parts of different winters, which can be anti-correlated and can reduce the sort of effect. But if you look from April to March, you know, if the last quarter of the year is bad, it's quite likely the first quarter of the next year will be bad. So what you see over this period with supply equal to demand, you see surpluses running up to about 40 terawatt hours a year and deficits running down to about minus 60 terawatt hours a year. Now have a look at this case here. Here's 3 years in a row with large deficits. If you want to fill those with storage, the storage has got to be in earlier years. Well, there's not enough in these years to do the job. And if we go back further, we start to get deficits. So in fact, we're going to have to store energy from right back here somewhere to fill these deficits. And then you can start to worry, what if these years are repeated very soon thereafter? And I'll come to that in a moment. So that's the basic underlying problem. Now, what do we need? We need hour-by-hour models with the best resolution available of wind and solar supply. And that's, thanks very much to Iain Staffell and collaborators, we're using Ninja Renewables data with wind and solar mixed 80-20. That's the mixture that minimizes the amount you have to curtail or store with this model and with our model of demand. Now, for demand, we've got a model from AFRI of 570 terawatt hours a year. It's put into the grid. So this is hard to recognize this number because it doesn't include electricity for electrolysis except for making hydrogen for storage. No, sorry, it doesn't include it. This is just customer demand with the losses added. Now, what are the issues with this? The first is 37 years enough? Now, I've plotted here with values we'll come to later, values you might want to use, with the levels in 123 terawatt hour hydrogen store filled by 89 gigawatts of electrolyzers. So this is allowing for inefficiencies and so on. Now you can see this level here, it is jumping up and down. And of course, it gives the impression here on the scale that it's full a lot of the time, but it's jumping up and down every hour. And obviously you can't see that by eye. But notice what happens. There's those years I showed that look bad. Here they are. Tremendous fall. And then you notice if I'd studied these 23 years here instead of these 37 years here, I'd have reached totally different conclusions about the need for storage by a factor of 2, in fact. So we started to worry 37 years is not enough. And I went to the Met Office and said, is it enough? And this is rather amazing. Our Prime Minister before last told us that we will become the Saudi Arabia of wind. But it turns out, when I asked the Met Office, is 37 years enough? They said, we've never been asked that question. Yet the government is embarking on high wind. What they did is they went back and looked at historical data back to the 19th century, actually, and they simulated 10,000 winters, and they said, no, it isn't, which we'd already guessed from this plot here. In fact, they said that in this particular period, there is a 10% chance per decade of finding a winter month with less wind than in any of the winter months we studied. So we don't know how to deal with that. So I've dealt with it by adding some contingency. I don't know if that contingency is enough, and we thought about other contingencies. But the interesting thing is it doesn't make much difference to the cost. And the reason for that is that the cost of storage, without the cost of the power put into storage, only contributes 15% to the cost of power. And the cost of the store only contributes a third of that. So the cost of the actual store only contributes 5% to the cost of power. So I can afford to put it up by 20%. Now, the other worry with supply is climate change. Now, many people have studied the effects of climate change, and you have papers saying there will be more solar in France and less wind, vice versa, in Germany or whatever. But when you look at those papers, they don't even agree on the sign in different countries. So what you must not do is average them, because you will get a result which is not representative of any of them individually. So the effect's very uncertain, although the authors who look at it all say that the interannual variability, the variability from year to year, is bigger than the uncertainty of the effects of climate change. And let's just hope it's covered by the contingency I've put in. Now for the demand, we've only got 1 year. We can't, but AFRI, as I said, modeled it on the weather in 2018. So we've repeated it 37 times. So this does not take into account detailed correlations between very cold weather and low wind, for example. The models that we've constructed are constructed models that with very high levels of heat have looked at historical data and saw what happened if I repeated years rather than matching every year, suggests that a broad brush for things like the wind-solar mixture or the amount of long-term storage is actually very insensitive to not taking the detailed correlations into account properly. But it clearly has some effect on shorter term. Now, for the model, you might say, what if 570 is not correct? So we looked at 440 and 700. And we did that. We took the AFRI profile and we shifted a lot of the heating, basically. We electrified heating a lot more in the high demand model and a lot less here, and shifted some other things around. And we got to results that have very different profiles. As we go from our 440 model to the 570, the ratio of demand in January to that in July increases by 8%. But the cost of electricity only goes up 1%. And the same is true when we go from 570 to 700. So as you go to these profiles with a more varied demand, because they've got a bigger difference between winter and summer, because there's more electrification of heating, it costs you more because you've got more variability, but not very much. It's only about 1% for each step between 400, actually 2% between 440 and 700. So we think this is reasonably reliable. Now, let me say something about the trade-off. There is the procedure. With a single store here, there is a trade-off between the size of the store and the rate at which you charge it. So let's look at this filling factor over here, and look at this period around 2011 when it's falling. So every time the wind's not blowing, it goes down, and then when it is blowing, the electrolyzers work and it goes up again, and so on. So if we put more electrolyzer power, the upward steps will get bigger and the bottom of this curve will be higher. And I could get away with a smaller store. On the other hand, if I had less electrolyzer power, I couldn't compensate for this fall so much, and I need a bigger store. So there is a trade-off between the size of store and the rate of the charging. And to find how to deal with that trade-off, you have to know the relative cost of storing and of charging and find the cost minimum. With several types of store, there's the issue of scheduling in them. I'll come back to that later. Now, let me now say something about the technologies that we've looked at. And I've divided those into 3 categories. Ones which are very expensive per unit stored. So you've got to cycle them very rapidly in order to recover the investment. If they're sitting idle too long, you go bankrupt. Then at the other end, there are ones that are very cheap in terms of storage cost. You can afford to have them sitting idle, storing energy for years. And I've shown with that picture of the interannual variability of surpluses and deficits, we're going to need such stores. And then there are things in the middle where you have to cycle weeks, in some cases months, to get back your stores, your investment, but they can't, you'd be bankrupt if you tried to use them for years. So we've gone through a lot of different types of stores here, and I'm not going to go through them all, except to say that we singled out 3, one from each class to study. We looked at batteries because lithium-ion batteries are well known, and we know how to study them, and they're being used today. In this category here, we looked at adiabatic compressed air energy storage, and the reason we did that is that it is capable on its own of just about of meeting all demand in the UK, and it has pretty high efficiency. And the various elements are at rather high TRL. Complete systems is not necessarily justified. There are two big complete systems working in China, as I'll say, but I put them at 7 to 8 here. So we took ACAS as an exemplar of these different things here. But these other ones, I mean, Carnot batteries, for example, these are big piles of rock that you blow hot air through and then you take it out again. They could store maybe a terawatt hour or two, but they look more expensive and less efficient than ACAS. So we took ACAS in this category. And in the bottom category, synthetic fuels, you can store terawatt hours, all right, but they're outclassed by ammonia and hydrogen for electricity storage. Hydrogen looks to be the best because ammonia is made from hydrogen, so it's more expensive, obviously, if it's made from hydrogen. And secondly, because you've got to make hydrogen first, it's less efficient. But the trouble with hydrogen, the potential onshore storage potential is very large, but it's limited to East Yorkshire, Cheshire, and Wessex. So you've got to worry about grid congestion if all the storage is there. So we also costed ammonia, which you can put anywhere, but it's quite a lot more expensive. So you probably live with grid congestion instead. So those are the technologies we looked at. So now, my slide, here we go. I'm going to go through step by step with hydrogen and then ACAS. And the batteries, I'm not going to go through the details. So for electrolyzers, there are three types: alkaline, polymer electrolyte, and solid oxide. Now, alkaline have been in operation since the 19th century. They're well known. They're commercially available, and they've mainly been used for making chlorine, which is much more demanding than making hydrogen because it's corrosive. So they're well understood. And, you know, if we had to rely on them, we could do it right now. Polymer electrode membranes, the trouble there is their availability is limited by the availability of iridium. That's really the only resource constraint we came across, so we'll come back to that. They're commercially available, but there's potential for improvement. Solid oxide, unfortunately, not yet demonstrated at scale, but they have a tremendous advantage. They can be operated reversibly. So when the wind's blowing, you can operate them as electrolyzers. And when the wind's not blowing and you want power, you can operate them as fuel cells. So you save a lot of cost if you do that. But the trouble is they haven't been demonstrated at scale. You can't do that with the others because the other type needed different types of catalysts going forward and going backwards. They can follow loads, but in the alkaline case, you need to operate above 20% of the minimum current. And we thought that was a bit of a problem, but it isn't because we've got hundreds of the damn things. So we can have them either operating at the optimum conditions or turned off. So we can get a very smooth variation. The problem is they do have to be switched on and off frequently. We worried about that, whether that would lead to corrosion. And the answer from the experts is almost certainly not, but it needs to be verified. Here are the efficiencies today, and then I've looked at future efficiencies. IRENA is for 2050, IEA just says future. Now, you can see these are the future numbers here, and we've taken 74%, which looks pretty reasonable here, and the results are not tremendously sensitive to that. What about the costs? Now, today, the costs are up at around $1,000 a kilowatt or more for solid oxide. These, by the way, are full system cost. What about the future? Now, IRENA think more or less everything will be under $200, so it seems, or $300 for solid oxide. But you've got to be careful, and IRENA gives a big range, 200 to 700. But when you read them carefully, IRENA says that's extremely dependent on the size of the modules and the scale of manufacture. And actually, they assume $450 as their best value. And just to give you an idea on the size of the modules today are typically 1 megawatt. If you go to 20 megawatt, which is certainly possible, they're 33%. It goes down 33%. And it goes down another factor of a third if you go to 100 megawatts. So it's very dependent on the size of the module and the scale of manufacturing. And Arena's a bit naughty. They put $200 in their summary table, but when you read it, it says 200, they say, if by 2050, cumulative production is 5 terawatts, it'll be 130. But if it's 1 terawatt, it'll be 307. In any case, we think 450 is pretty safe. We have statements which I can't reveal from manufacturers because they're commercially sensitive, which makes this 450 look pretty safe, and we've taken plus or minus 50%. What about the lifetime? This comes in, you've got to assume a discount rate and how long it operates. So here are today's lifetimes in thousands of hours, and these are the future predictions. Now, that doesn't look very long until you realize that in a third of the year, the electrolyzers are only operating about a third of the year. Most of the year, you're in surplus at the level of wind and solar we're at. Sorry, the other way around. So the load factor is low. So these numbers do correspond to 30 years. So we take a financial lifetime of 30 years. The output pressure, this seems a bit detailed, but I want to get into this to show you the level of detail we've been in. Here are the pressures today. Here, IRENA doesn't give, the IEA don't give predictions for the future. These are the predictions from IRENA for the future. Now, this number matters because before you store hydrogen, you've got to compress it. So the bigger power you can get out, pressure you can get out of the electrolyzer, the less you have to put into the store, and the cheaper the store. We've assumed 30 per bar, although that looks conservative. Now, what about the underground storage? Unfortunately, my slide is stuck. Oh, here we go. Sticks and then changes too. Here we go. So we have assumed for storage, we've taken costs. Well, first of all, we're assuming it's being stored in very large underground solution mine salt caverns. Now, these caverns are made by going deep underground. There's a split scale here. The ones that we've looked at from this H21 study, the top of the caverns at about 1,700 meters, so it's a mile underground. They're about 100 meters high. And there's a layer of whatever material here, and then salt. And you pump down water, it dissolves the salt, and you take out brine. That's what solution mines need. Now, H21, it's a consortium that involves Scottish Power, Equinor, and other pretty reputable bodies. In this 600-page report, made a study of clusters of 10 300,000 cubic meters solution mine salt caverns. And these 10 caverns, they're in a cluster, they share common surface facilities, which is commonly done, actually. And there are people with more than this. I'll give an example later. Now, in these clusters, each cluster stores about 1.22 terawatt hours with lower heating value. So each cavern is storing 122 gigawatt hours. So have we got enough? So this is what the British Geological Survey tells us. If we want caverns that are capable of storing 120 gigawatt hours or more, this is the amount we've got. We've got a potential in East Yorkshire alone for 1,200 terawatt hours. And we saw it earlier, actually what we want is a small fraction of that. So there is enough potential out there. Now, H21 have made a study and they say it's going to cost £247 per megawatt hour to the capital cost of this cavern. But given recent lack of experience and the underground hazards, it's very, very difficult, as I know from my experience as Director General of CERN, actually, to cost underground work. We're going to take their value as the low value. We're going to take 50% higher as a base value and 100% higher as a high value. Now, what about other estimates in the literature? Comparison is extremely difficult because it depends on the geology, whether you have good salt, we do in the UK, and the geography, the distance to brine disposal. These guys assume 10 miles, and there's plenty of caverns in East Yorkshire within 10 miles of the shore. And it depends sensitively on the size. And this is really critical. So this is a study that Argonne did for DOE, which is essentially the only study in the literature with enough detail to allow a serious comparison. And Argonne studied size, this is for rock caverns, so that's irrelevant, but this is for salt caverns of different sizes, and this is the storage and stored capacity cost per kilogram of hydrogen. Now you can see it's falling, but rather accurately, like 1 over the square root of the mass stored. So that really matters. Some of you will know that MIT recently made a study of storage, and I couldn't understand their very high values compared to what we take. And the reason is they were actually relying on this study, but they assumed 500 tons being stored, I think. Can't remember the exact value, whatever is that blot is. Whereas we're assuming about 5,000 tons, and we're up here. And actually, the H21 value lies really well on this curve. So there's a really important message here. You cannot go to the literature and take stores and average them. You've got to allow for the size of the system. We'll see that again in a minute. Now, what about the generation of power from hydrogen? It's a similar message. I'm frozen again. Why is my, here we go. Right, so I've skipped 2 again. Conversion, go back. Okay, so we look very carefully at PEM cells. Now let me begin by saying that chem cells, polymer electromembrane cells, as fuel cells, have been studied extremely carefully for use in vehicles, but they have not been studied so carefully for use in power generation, and it's quite difficult to get estimates. But just to give you an idea, DOE thinks that at a scale of 20 gigawatts per year, this cost of PEM cells for power generation for heavy good vehicles could fall to under $100 a kilowatt, actually before 2030. Now, cells designed for use in power generation will be more expensive. They're unlikely to be manufactured at the same scale. The balance of plant costs have to be added, and there are somewhat different constraints. But anyway, this sort of shows you the sort of thing we should be thinking about. If you go to the literature, the best survey we can find, although we've made estimates of our own that I'll describe in a minute, give low, medium, and high costs of 340, 425, and 528. That's including a 50% markup and 25% for installation. So those are full costs. That's cheaper than using turbines. The literature talks about using combined cycle turbines and so on. Now, just before I move to the next idea, to say there are very detailed breakdowns in the literature of the cost of PEM cells that work on natural gas, which first have to break the natural gas down into hydrogen. So we took to those estimates, or rather Anthony Kuchenak at Imperial did, stripped out everything to do with hydrogen, and he came back to me and said he thought this 425 was a very good value, possibly conservative. So this is what we've taken. Now, I'll tell you where we got the low value. Oh no, yeah, it's down here. That's what they got. But we also thought about 4-stroke engines. Now, if you mention 4-stroke engines in power generation, people say, if 4-stroke engines are cheap, why are they not being used with natural gas? And the answer is that they are increasingly. There is a 600 megawatt power station in Jordan powered by 4-stroke engines running on gas. And they're quite a lot of small units put together. There's a big unit in Tennessee also, by the way, whose cost we've looked at. Now, 4-stroke engines, you have a lot of relatively small units, but that's quite what you want with renewables, because you want flexibility. And if you have a lot of small units, you can turn them on and off. And we think they could be cheaper from PEM. We asked an expert at BP, and he came back with $300. And we then talked to JCB. JCB have designed, they've built a prototype digger running on hydrogen. And it's quite interesting. They've found a different operating regime. Most of the people who've looked at hydrogen four-stroke engines have started with a petrol engine and adjusted it. But JCB said, well, we're going to worry about NOx emissions. And to do that, they went to a leaner burn, more air, less gas. And with the leaner burn, they found actually much cheaper overall costs. So we're going to go below NREL and we take a low cost of 300 and then we added 50% for the high cost. Now let me tell you what we did for compressed air. Now, first of all, let me tell you how it works. So you have a motor that compresses air, pushes air into a geological cavity, brings it out again through an expander, and it drives a turbine and generates electricity. Now, the problem is that when you compress air, as you know, when you pump up your bicycle, it gets hot. The converse is true. When you expand it, it gets cold. And if you didn't supply heat at the expander stage, this would freeze. So to date, there are two large systems of compressed air, one in Germany and one in the US, which burn natural gas to stop it freezing. That's just called compressed air energy storage. Advanced compressed air means you store the heat and put it back again. Actually, the heat stores almost all the energy, and the air stores exergy, the ability to do work. So it's not quite what you think. Now, as I said, there are two large systems, 300 megawatts, if you think that's of electrical output, operating in China since May and September, respectively, last year. And as far as I know, operating quite well. Now, you can then ask, what's the cost for compressed air? And you cannot give a generic cost. And the reason is it's very dependent on the pressure range. And if you're going to store in a geological cavity, which you've got to do if you want it to be large scale, that depends on how deep you go. So again, you have to be very careful. People say, oh, we assume we can get this pressure range. That pressure range may not be possible in certain conditions. Secondly, it depends on the design, the stages of compression and expansion and how the heat is stored. Now, we decided that we wanted to store heat in water because it's much, much cheaper than the alternative with which molten salts. And to do that, you need 6 stages of compression at the conditions we're in, which I'll show you on the next slide. And you take out the heat after each stage and you cool it down again. So you have a number of stages of compression. So it depends on these design features and how you store water. And the last thing is the cost of compressors. You find in the literature compressors cost X per kilowatt hour, but in fact, the cost grows like the power to the 0.6, something like that. So the cost per kilowatt goes down like 1 over the 0.4. So there is no generic cost. The underground capacity in Great Britain is perhaps enough for ACAS that would deliver 20 terawatt hours a year of electric, but that would start to encroach on other needs for underground storage. Now, what do we actually take? Again, it's skipping 2 stores. How? Here we go. So here's the pressure range. So this is in East Yorkshire. This is the depth going in this direction. You can't get below a certain pressure or the cavern collapses. And you can't get above it or it also collapses. So in fact, if you go to rather shallow caverns, you've got a rather limited range of pressure. So you're limited in what you can do. So we looked at 1,000 meters, which is below the top of the salt. And we looked at the H21 of 1,700 meters, which is about 200 meters above the bottom of the salt. So we looked here with a pressure range something like this, and we split the difference between what we found at these 2 different depths. So we're looking at compression in 6 stages, expansion in 6 stages. This has to be supported by 7.5 gigawatt hours of thermal storage. Oh yes, there is in each cavern 10 gigawatt hours of work. You need to store 7.5 gigawatt hours of thermal storage, and you can deliver 6.8 of electricity. Of course, you actually get more energy than this in compression. That could have other use, but we haven't modeled that. Now, how do we cost this? We took the H21 costs, stripped out those that were strictly related to hydrogen, pro-rated the overheads. So we worked out the H21 cost for a cavern for storing compressed air, and we multiplied it by 50%, just as we did for hydrogen. Water pit storage, we took the actual cost for very, very large stores in Denmark, and in fact, we've taken a rather conservative function of them. Compressors and expanders, we have quotes from suppliers, which are much lower than those in the literature, but I've actually seen these quotes. So they're real quotes, but they are not for delivery in the UK. They are for complete systems that you could plug in and use, but they don't include site preparation. So we scaled them up, but of course they'll go down when the scale of manufacture goes up. So we're still, as I put a health warning in here, in discussion with manufacturers about the proper cost of compressors, because it also depends if we try to share them between one huge compressor for 10 caverns or 6 compressors for each of 10 caverns in the cluster. And it makes a big difference for these scaling laws. So it's a little bit uncertain here. But on the sort of negative side, you can buy reversible compressors and expanders. They're out there in the market, actually, and that would save costs, but we have not assumed that. So we've tended to be rather conservative. Of course, it's a huge jump from 2 300 megawatt systems working in China to a large number of 6.8 gigawatt systems, which is what we want. But it's also a big jump for hydrogen storage and for wind and solar generation. On the other hand, these are much better known and better understood. Now, let me now come to the results. So with a single type of store, so this is hydrogen with battery storage costed for grid services, and £3, which adds about £1 per megawatt hour to the average cost of power, and for the transmission from wind and solar farms to stores, which probably conservatively adds about £3. So this is what we find as this bump is an artifact of Excel. I need to put in the points so it doesn't look odd. This is what we find with the low cost. This is with the medium cost, with the high cost, as a function of the level of wind and solar generation. So down here, this is the threshold. At this point, this is the minimum value at which storage only can meet demand. And to do so, you have to store all of every surplus. And that gives you then the minimum size, a very large store actually, but it's extremely expensive. As you go up above this threshold, the amount you have to store drops rapidly, the size of the store drops rapidly. So the size of storage drops rapidly above the threshold here, but the cost of wind and solar goes up because by assumption here, we're using more of it. So there is a rather flat minimum. Now, what is this dotted surplus sold curve? So except actually at the threshold where you're storing everything, there is inevitably a surplus that you can't store either because the store is full or because there isn't enough electrolyzer power. So this surplus store assumes unrealistically that the entire surplus is stored at cost. That's not realistic, and it's increasingly improbable as generation increases. But I put it here to show the indicate of possible savings from co-production. And if we were looking at the use of storage for other purposes, we've got hydrogen here sort of generated for free, if you like, which you could use for other purposes. And that will give you some indication of the importance of thinking about that. Now, what happens if you add baseload? Adding baseload will increase the cost of the average cost, unless it costs less per megawatt hour than the average cost without it. And that is a theorem. And the reason it's a theorem is if we think about adding, let's say we add 200 terawatt hours a year of baseload. If those 200 terawatt hours had exactly the same profile of demand, which of course they don't, but if they had the same profile of demand, all we'd have done is scale down the size of demand. The scale of the wind and solar we need would go down proportionately, and the cost of the power produced by wind, solar, and storage per megawatt hour would be the same. But the base load is not the same profile as the demand. On the contrary, it's going to be flat by definition if it's base load. So if you remove a constant amount, you've produced a system with a smaller demand, but it's much more volatile, the demand, and it's more expensive to meet it. So this means that if you're going to, it's not enough that, well, whatever you think the cost of nuclear is, it be lower than the costs we're finding up here. It's got to be lower by some margin. We looked at using ammonia only instead of hydrogen only. It's more expensive by something, it depends on exactly what you assume, but it's at least £5 a megawatt hour. That's probably not a price worth paying to avoid grid congestion. We also asked, could you do it entirely with ACAS? And the answer is with great difficulty. The cost would be higher, and you would exhaust the storage capacity in the UK, more or less, because ACAS doesn't want to store things for these very long periods that we found were necessary. Now let's come to the multiple types of store, and then I'm getting close to the end. To model and operate with several types of store, the operators got to decide when there's a surplus, which type of store do I put it into? When there's a deficit, which type of store do I call upon? The studies in the literature use hindsight to allocate things to stores. So that means in practice, to do what they do, you'd have to have perfect foresight, which you don't have. So you've got to invent something else. So to give an example of what we did, let's think about two types of store, hydrogen and ACAS. ACAS is more efficient, but it's got a higher cost. If it was cheaper than ACAS and hydrogen and more efficient, you wouldn't be losing hydrogen, obviously. So if we start with hydrogen, you've got to pay the capital value of the hydrogen. If you add ACAS, there's got to be that it lowers the cost of the hydrogen store. It decreases the size and the cost of the hydrogen store by more than it costs to add ACAS. This is most likely to happen if ACAS is normally, and I'll qualify that in a moment, given priority in storing surpluses and discharging energy to fill deficits. And the reason is that if it's given priority, it will deliver, that maximizes the amount of energy that it will store and deliver, and therefore it minimizes the amount of energy that has to be stored and delivered by hydrogen, and it reduces the size of the hydrogen system. At the same time, since ACAS is more efficient, if it's delivering more energy, you need less wind and solar, and the power of that goes down. Now, I say normally because, following Stan's suggestion, when the ACAS store is nearly full or empty, we shift priority. This has a rather smaller, in order to prevent the hydrogen store falling out. This has a relatively small effect on the average cost of power, but it changes the demands on each store to absorb and provide power. Now, what's the result? With the conservative costs for compressed air, adding it lowers the cost by 1% or 2%. With the aggressive cost, it lowers it by a whopping 7%. And in which case, actually, although the ACAS store is relatively small, it's cycling so often it's delivering most of the energy. So that's quite interesting. We are exploring the sensitivity to the efficiency because we were taking ACAS to be an exemplar, a proxy for other terms of medium-term turnover storage. But in fact, it's much more efficient than the alternatives. And it's not actually obvious to me that if things less efficient than ACAS, say 55% efficient stores, would lower the cost. There's an important point here, which is the cost minima in the multi-parameter space. And with ACAS and hydrogen, you've got 6 parameters altogether. Like all minima, it's flat and it's very broad. And this means that you can vary the relative sizes of the ACAS and hydrogen stores and the amount of the parameters quite a bit without changing the costs. And this gives rather important scope for not just looking at costs, but for considering buildability, operability, and the reliability in designing the system. In fact, even if this put the cost up a bit, it might be worth doing. There is a final point here about multiple stores, and I'm sorry I'm going so long over time, which is that in order to use any of these systems where you coordinate the use of hydrogen and ACAS, you've got to have colossal coordination between the generators of power and the operators, which in the present system simply wouldn't happen. So we're going to have to reform markets. I'll return to that briefly. Now, what are the next steps? So quickly, more use on work on scheduling. In fact, it'd be very interesting with fixed costs. If you have hindsight, if everything else is fixed, you can distribute the use of the stores to get an absolute minimum of the costs. And then you can see whether Stan's procedure or our procedure, whatever procedure, how close it approaches that minimum. That will be very interesting. You want to look at the whole system, taking account of location of demand, supply, and storage. And this is the question of grid congestion. We'd like to take into use other uses of hydrogen, but opinions differ enormously on how much hydrogen we'll need, and we don't know the daily profile. And we'd like to put correlations between weather and demand, but it'd be very difficult to go back over the 37 years of data putting that in. We need more work on costs and timing. On the ACOS cost, that's going on. We're doing it right now as a final step. And we have to look at the costs of other the competitors for medium-term turnover stores. What about the investment? In the all-hydrogen case with 550 terawatt-hours demand, we're going to need about 200 gigawatts of wind and solar capacity. According to Bayes' projections, to have that in place by 2040, and some will have to be in place earlier, some later to get to 2050, that'll cost about 210 billion. That's not a huge amount, actually, but that's got to be in place before we switch off the CO2 emitting sources, or we won't be able to meet demand. To get that amount, the rate of insulation will have to increase. National Grid's scenarios, some of them have large amounts, suggest it's possible, but the rate observed in the last few years is going to have to increase. We're going to need something like 100 billion in hydrogen production, storage, and conversion. That's with the costs that we've been assuming. And in addition, for enlarging and strengthening the grid, the National Grid thinks that between now and 2050, we're going to need about 100 billion. And we're going to have to work on markets. If we don't make the changes that are needed soon in order to encourage deployment and avoid infrastructure lock-in, we'll get locked into the wrong infrastructure. We need markets that encourage a mix of wind and solar supply, which is partly coming directly to the consumer at very low cost, and partly coming via storage at very low marginal cost, but extremely high absolute cost. And the question is, the market at the moment, somebody's got to pay for this storage, the high cost storage. Without it, the system won't work. But nobody's going to build it unless they're properly recompensed for it. And it's going to need close collaboration, as I said. We need R&D. What R&D do we need? It's too late, in my opinion, barring miracles, and I'll mention one possible miracle, for new science to make a major contribution by 2050. The Elizabeth line just came into operation. It was actually first proposed by Cecil Parkinson, if you can remember who he was, in the 1980s. We're very slow to do things in this country, and building large infrastructures takes time. So I don't think that new science can make a major contribution, but it's important for the long term, and there is one miracle that could do it. You can synthesize ammonia directly from air and water. It can be done in the lab, but it's extremely slow and expensive. If some genius could find a way of doing it cheaply at large scale, it would be transformative, and that might change things. But meanwhile, there's huge scope for improving existing technologies, combining them in new ways, e.g. in winter integrated storage. I don't have time to say what that is, in reversible electrolyzers, fuel cells, compressors, and expanders. And there are real steps like reducing PEM and electrolyzers. This is the only fundamental resource issue that we came up against. I mean, the IEA has written a many hundred-page resource paper on resource challenges to the energy transition, and their conclusion is that there can be bottlenecks which slow down things, but there are very few fundamental issues, and the only one we found was iridium. We need demonstrators to identify and solve integration issues. Now, Bayes has got this idea. They're funding a certain number of demonstrators, but they haven't got the idea of the scale. They've been putting money into demonstrators of systems that can produce sort of a few gigawatt hours. Now, that's very nice, and these people might make money with arbitrage, but they're not going to crack the problem. Bayes doesn't get it. We're going to need tens of terawatt hours of large-scale storage, and if we don't get on not just demonstrating it, but building it, it's not going to be there. And we've got to build it to get the cost down. Now, here is a thing that politicians really like. We're very well positioned in this space in the UK. INEOS, ex-ICI, have been making alkaline electrolyzers for hydrogen production since the 19th century, and they're just moving into, for chlorine production, they are just moving into hydrogen production. ITM make PEM electrolyzers. Ceres are the world's leading designer of solid oxide electrolyzers. Underground storage, I've quoted H21, they'd love to build these things. And Innovin, it's a branch of INEOS, have planning permission for a cluster of 17 350,000 cubic meters salt caverns in Cheshire to store natural gas. We've been talking to them about their costs and what they want to do. They've applied to change the planning permission to allow them to store hydrogen. But they say, we're not going to do any of these things because there's no business case unless we get some encouragement. By the way, they're also ready to build large-scale ACAS. They have plans for that. But, where's the business case? Power generation, there are lots of companies, including the giant Johnson Matthey, in the supply chain for PEM cells, as they are for electrolyzers. Ceres designs solid oxide electrolyzers, and JCB, as I've said, have produced a prototype four-stroke hydrogen engine. Come on, why won't it change slide? The second line, I'm on the conclusions now. So before I briefly say something about the conclusions, let me say something about the status of this report. Now, as many of you know, some of you know, this report's been going on for years, getting on for 4 years. The delays have been multiple. Initially, it was because the idea was to put together a small group, do a literature review, and write up a policy briefing for ministers on storage. But the more those of us involved looked at it, the more we thought that large-scale storage has never been studied properly. So this turned into, I don't want that. This turned into a research project. So that's given a lot of delays. There have been other delays. In the last few months, the guy who's doing the modeling took 2 months paternity leave without me knowing it was going to happen. And more recently, I've been fighting with the Royal Society about what the nature of the report should be. So what we decided, we did produce a 250-page report, but it's so long and so detailed, it's lots of things that we need to refer to, but nobody, even the experts in the industry, will want to read all of it, but they will want to refer to it. So what we've decided now is we're going to produce a sort of probably 60, 70-page policy brief, not a policy brief, a paper at the right level for industry experts and academic experts, with the detailed material put on the web as supplementary material. And we're going to produce a policy briefing, which is going to be at the level for ministers. So that's where we are. So the conclusions are where I started. We could meet demand at what I think here is a reasonable cost. And the alternatives, there aren't any alternatives as far as I can tell. They're just too expensive. So I actually think we're going to have to go down this route. And I think the primary thing that's needed is for somebody out there to recognize that we're going to need very large-scale storage, but no other source can complement large-scale wind and solar at a comparable cost. And we need to get on with it. That's it. Thank you very much. I shall stop sharing if I can find out how.
Chris, can you hear me?
Yes, I can hear you.
Well, that's very good.
Sorry, I've gone way over time, but I haven't given this talk in this version before.
So thank you very much. It's extremely interesting. Chris, I think we should press on.
Yeah.
But we will gather our sort of questions together, and we'll continue this conversation. It's all exceptionally interesting, especially to me, the point about some economic stimulus is going to be required from the government for economic reasons. People won't do it on their own. Thank you very much. We will press on. Next speaker is going to be Tom Bransden from the ESO. Still anything to do with National Grid?
Yes,
we're
on the same as
we're going to work out how we make things happen after that. Thank you, Chris.
I'm going to try and talk and set up at the same time. Is that showing the full screen? No? Okay. Hi everyone. So I'm another engineer and also from the ESO. And thank you, Sharuk, for giving background on the ESO earlier. So I work in the EMR modeling team, and we look at capacity adequacy. So I think it was highlighted earlier by Chris. We work to secure the system on the GB reliability standard, which is currently 3 hours of loss of load expectation. But our team also models capacity adequacy right through from the week ahead operational margins. So looking to ensure the supply is matching demand in terms of the wind forecast in a given week, but also the generation forecast and the expected electricity demand. We also do the modeling for the winter outlook. So looking at the winter ahead and making sure that the loss of load expectation is within the reliability standard. We also modeled the capacity to secure for the 1 year ahead and the 4 year ahead capacity auctions. So again, to the GB reliability standard. And we've recently stood up a new team called Net Zero Adequacy Modeling, which is looking at longer term time horizons in a more decarbonized GB system. So there's a lot of parallel to the talk which Chris just gave, which was very interesting, a very detailed view of the future and some very interesting discussions around potential technologies and so on, particularly as an engineer, I find very interesting. I'm going to hopefully provide a view of some of the uncertainties that go into this modeling and hopefully complementary to the presentation previously. So I think Jim mentioned in terms of the increasing uncertainties in his talk, and particularly how you can conceptualize risks in a systematic way. So I think that's something hopefully will come out through this presentation, where we have increasing variability as we transition to a more renewable system, particularly from renewable generation. I'm going to focus on variability in terms of days through to years, in terms of renewable output and how we manage that appropriately. So you can see here how we view variability in how we manage and balance the system from minutes through to days and years. So you see that the scale of the energy balancing is from megawatt hours through to terawatt hours. Lots of mention of terawatt hours in the previous presentation, and that will continue here, where we're focusing on managing variability of oversupply and undersupply of renewables on the scale of days through to years. This will obviously feed into current market development activity, particularly BASE's review of electricity market arrangements, looking at the design of new markets that incentivize these sorts of terawatt-hour scale balancing technologies, but also innovation funding requirements in terms of technologies that are not quite there in terms of the required scale. I think Chris mentioned that on a couple of his last slides. We use some existing adequacy modeling techniques, including time sequential Monte Carlo simulation that look at how you meet a certain reliability standard over time. However, many of the inputs, as highlighted through some of the presentations today, are increasingly uncertain and variable over the timescales we're looking at. So just to illustrate some of the situations we're looking at in terms of managing the oversupply and undersupply from wind, this is an undersupply case in 2035 in January, using weather data from 2017. And you can see a consistent period where demand exceeds supply in terms of the renewable generation output. We also have the contribution of interconnectors in this case, and we have contributions from nuclear. This is the sort of situation we're thinking about when it comes to adequacy, and we're trying to minimize the unserved energy on the system in order to reach a certain reliability metric and achieve a certain risk level. This is from our operability strategy report, which we publish early each year, which looks to the 2035 power system and how we manage the risks in that particular case. And as this shows, oversupply will also become an increasingly important feature of the power system in terms of making sure that the costs of operating the system are not prohibitive, so we're not constraining renewables to the extent that it becomes very, very expensive to operate the system. So we're both looking at oversupply and undersupply from renewables in balancing the system.
Very simple question. Here, the bar here.
This one?
Yeah.
Thank you. So with adequacy in mind on the timescales of 2030s and 2040s, we recently commissioned AFRY for a resource adequacy study into the 2030s, which was published late last year. That study found that there was no trade-off between adequacy and net zero. However, we do need new, clean, reliable technologies, as I'm sure I'm preaching to the converted in this audience. We looked at a number of portfolios which could be required in a future system, and we found that 6-hour batteries alone weren't enough to meet adequacy objectives. And in fact, one clean, reliable, new technology at least was required to do so. We welcome any feedback anyone has on the study through the Dropbox email address I provided below, and it's also in the study. So to dive into some of the areas which are uncertain that are potentially providing different levels of balancing requirements in terms of gigawatts of output from your technologies, in terms of the amount of terawatt hours that you're storing, and so on. One obvious one is the renewable generation output that you're going to get. So the weather data that inputs into that, and particularly the wind speed and the irradiance data, that is uncertain in terms of how it's driven by different climate projections and different climate models. Another uncertainty is what the future wind turbine fleet will look like, and particularly the power curves of these larger and larger turbines. Many of those are proprietary information on the timescale that we're looking at, and we need to understand the potential range in terms of what the output could be from those turbines. Another that was highlighted by Chris in his presentation is the reliable reliance on interconnection contributions during a GB stress period. The reality is that we will have increasing quantities of interconnection on the system, and so understanding the contributions of those interconnectors is going to become increasingly important. In particular, the correlation of weather events between GB and other interconnected countries is going to be an increasingly important factor, and how markets operate during stress periods will equally become important. So currently, many market models, including our own, assume that markets operate perfectly efficiently and the market participants have perfect foresight. Some of those assumptions are going to need to be challenged as we see increasing contributions from renewables and interconnection. Finally, in terms of electricity demand forecasts, there's naturally going to be an increasingly electrified fleet of electric vehicles and heat pumps for both transport and heating. How that is deployed is again another variable factor. We're going to be increasingly interested in the contribution of demand, or the amount of demand during periods where we have low renewable output or very high renewable output, while in the past we've been more focused on average cold spell peak demand. We're going to have to look more at different demand shapes over the year. So to focus on weather and its interaction with climatology, Jim mentioned the increasingly long-tailed distributions that we start to see with these extreme weather events. With the adequacy problem and oversupply problem, we're looking at persistent wind droughts and looking at persistent oversupply events. One of the key challenges, as was alluded to by Chris, is how do you estimate the range of variability to get here? So you see here in the graph that there's a range of severity you get in terms of those wind drought events during winter. You'll see that it varies in terms of the 1 in 100-year return period, depending on the temperature assumed in the climate model. But this is just one climate model. And if you look at multiple climate models, you have multiple ranges, and managing that uncertainty in terms of how it affects your weather data and your renewable generation is something that simply isn't used within existing models. So trying to represent that statistically is really important. But on top of that, how we represent the risk, particularly to stakeholders, has got to change. So we currently use expectation metrics, loss of load expectation, expected energy unserved, but increasingly we'll have to look at metrics that manage the tails of these distributions, which are not Gaussian. So I think Chris's paper with a conditional value of risk was mentioned. There's a paper that I've referenced below that also looks at that. These are sorts of things we'll need to grapple with in terms of how statistically useful they are, but also how can we express them to stakeholders. We have a reliability standard, which is loss of load expectation for 3 hours a year currently. How do we integrate these new risk metrics into our modeling, but also in presenting them to decision makers who are setting up these new markets? So the Met Office study that published the graph on the right also produced the data set in terms of different extreme weather scenarios. So they looked at a summer wind drought, a winter wind drought, and then also an over-generation period. So these are some of the events that we're going to be particularly interested. They used a range of climate projections, but they provided their data at a daily resolution. Many of the modeling techniques we use to assess adequacy and otherwise are based on hourly or sub-hourly resolution. And one of the challenges they found was downscaling that data from daily to hourly. They could do that for temperature, so for surface level temperature statistics, but they found it more difficult for wind speed. And naturally, there's going to be correlations between each of those weather variables, and making sure that you maintain those correlations while also maintaining the summary statistics of the weather is critical to making sure that we're simulating with correct data sets. Now, once you actually have what you consider to be a reasonable range of potential weather under different climate projections, then you have the question of what is the technology, and particularly wind and solar, which under our future energy scenarios is going to be increasingly built. One particular sensitivity is the wind turbine itself and the power curve. So currently we're seeing turbines on the system that are of the order of 150 meters offshore. Some of the newer ones that are being built on projects towards the end of the 2020s will be 235, 240 meters. The power curves of these machines are radically changing, and the amount that they produce at low wind speeds is particularly increasing. And that's something that is a very big input in terms of how it affects the models of adequacy and in terms of the low wind speed production of those turbines. The location of the wind farms is also very important. So geographical dispersion of wind farms can change the GB output of wind generation depending what's simulated. You'll see here that where there's low wind speeds on the east coast or the North Sea, where a lot of GB's current fleet of offshore wind is connected and a lot of where it's projected to be built. When there's low wind speeds there's higher wind speeds in the Celtic Sea, which is another candidate area for where wind farms will be built. And it'll be important to capture a potential range of where those wind farms can be built, particularly on the timescales of 2035, 2040s, where we don't have transmission connection requests and so on that give us a bit more confidence where these are going to be located. The correlation of weather events is also an important factor between GB and interconnected countries. So as I mentioned previously, the interconnection between us and our neighbours will be an increasing driver of uncertainties in our models. You can see from this graph that Dunkelflatter events between GB and our neighbours in the Baltic and North Seas are not necessarily correlated. So you see it's quite correlated between us, Belgium, Ireland, and the Netherlands, but it's actually less correlated when it comes to countries like Denmark and Norway, where there are interconnectors being built as we speak. And so understanding the correlation between output of renewable fleets, which will be increasingly built in these countries, but also their demand as their demand is increasingly electrified, will be very, very important. We currently use pan-European market modeling to capture some of this uncertainty. However, as I mentioned before, we use perfect market assumptions. So particularly with the advent of new geopolitical risks, I think I wouldn't take the same stance that Chris did in terms of no reliance on interconnectors, but it's important to understand and present the uncertainty that these factors have to decision makers and to policy makers. We need to start to capture some of the uncertainties in our market assumptions and also our geopolitical projections. Now, in terms of electricity demand forecasts, we currently primarily use forecasts of average cold spell peaks of demand in a lot of our simulations. That will need to become more granular as we look at demand correlated with weather during very persistent wind droughts and overgeneration events. The demand response that is able to what we call demand destruction during those events will be important. So if people choose not to drive their electric vehicles when there's a wind drought, that could have a material effect on the amount of terawatt-hour scale balancing that's required. For instance, we'll be less interested in terms of the terawatt-hour scale balancing in terms of intraday flexibility. It's more about how much you can shift outside of that weather period. You'll see here that there are increasingly sophisticated models of short-term and medium-term electricity demand. So, for instance, this shows a GAM model, the reliability diagram there. We're starting to see higher and higher skill of GAM models, of gradient boosted tree models, these sorts of statistical learning models that can achieve quite high skill and high reliability in terms of what you can forecast. We're not necessarily expecting that will be the same sorts of models that are required on the scale of 2030s and 2040s, but currently we're just using scaling factors between peak demand and historical time series. So the more sophistication, the more understanding we can have of these correlations will be really useful. And finally, I'm not going to go into this because it was a very comprehensive treatment by Chris in terms of the cost of different technologies. This is a graph from actually in Staffell and a colleague's book, which looks at the cost down curves for different existing technologies or learning curves. These are the sorts of curves that we will need to build for the terawatt-hour scale balancing technologies. However, as was very well alluded to, there's a great deal of uncertainty in terms of what those might be. And there's also interactions between sectors, so hydrogen being used for multiple sectors, both power, potentially industrial and chemical uses, and so on. What we need as an electricity system operator is to help understand the portfolio is going to be the lowest cost electricity consumers in terms of delivering the services that we need. And so any techniques that can be used to quantify the uncertainty in these costs, but also in how these systems will deliver, is very important for us. So to conclude, the longer-term balancing in terms of managing oversupply and undersupply from renewable generation on the order of days through to months is dependent on a number of factors. Many of these factors are highly variable. There are unknown unknowns as well as known unknowns, and we need to start to quantify those ranges within our modelling and use appropriate statistical techniques. We have decadal weather events of these persistent wind droughts and overgenerations. We also have the uncertainty due to interconnection, where we have potentially imperfect market operation during correlated stress periods between countries. We have technology characteristics of wind power and also solar generation. We need to develop electricity demand forecasts that give us more confidence in the range of consumption during low renewable output periods. And finally, we need to make sure there is a low-cost portfolio that provides these services. So we need to understand what the costs are and the ranges of those costs, but we also need to understand how those will dispatch in the system. So these technologies will dispatch within a market environment. There needs to be a feedback loop between the development of these new markets and also what the operational strategies of these new technologies will be. Thank you very much.
Tom, thank you very much. We've got just time for a quick question. That talk's very nice. It complimented expressions earlier talk also. Very attractive way. Quick question from Jim.
Yeah, one of the things that I microphone.
Hello. Oh, I have to pass the microphone to Jim. I'm sorry, this is just beyond my technology capabilities. Yes,
It takes a long time to do this. Yeah, one of the things I would say here, I love the talk, first of all. I think that what you say emphasizes the fact that very often, you know, you pinpointed certain points where there were going to be certain types of crises, like still cold days. Things are a standard thing. So if you actually communicate various things like that, scenarios of combinations of things, then it's much more likely that you're going to get uncertainties associated with those combinations, right? So, for example, the Met Office can, given a particular climate situation, do simulations associated with things associated with different elements of weather, but they tend not to do that unless they're asked for it. Right? So I think one of the cultural things I think we should get into is just asking for things, thinking about what's going to be absolutely critical times, and ask for forecasts of that rather than just working on their assumptions. It's not really a question.
Thank you. Yeah, I totally agree. I think we've collaborated with the Met Office, as you might imagine, and we've spoken to them about these sorts of data sets, and we're looking to improve the way we use weather data in particular and capturing a full range of uncertainty. As I said, when that study was completed, the data sets weren't quite at the resolution that we wanted in terms of granularity, particularly temporal granularity. But it's something that we have ongoing discussions with them in particular, and it's looking at whether the current historical data sets of 37 years, 40 years are often numbers that are referred to. Is that appropriate, and should we be using all of that data set? Should we be looking just from the last 30 years, just from the last 20 years, because there's been already a change in the climate that means that the weather we're projecting is not realistic. And then, of course, when we look decades ahead, how are we adjusting those based on different climate projections and so on? Exactly.
So again, thank you very much. We're going to move on. Okay, now a couple of things. Our third speaker is Iain Staffell, whom everybody knows. He's not yet told me what he's talking about, but it's something to do with storage. A couple of things. Chris D tells me we've got a hard constraint that we have to start serving wine, drinking wine at 5:30. I don't quite understand why that's a hard constraint, but we're going to let Iain go for 15 minutes, and then we'll take a decision. One decision might be to grab our glasses of wine if we have to and bring them back here, or Iain can say the rest of what he wants to say tomorrow morning. But 15 minutes, you say, will allow you to say something in particular. I'm going to give this to you. I don't know what you're doing. Have it anyway.
Well, I hope it is broadcasting my sound. Well, thank you very much for the introduction. Yes, so I am the only thing that stands between you and the alcohol. And we've also had two very interesting presentations. Yeah, one covering the sort of theoretical calculation of ultra-long, ultra-large amount of storage, and then one, the more sort of practical near-term approach of how to get there. So there's possibly very little additional for me to say. So thank you all for this. There's one key point in my presentation I wanted to make, which is why I hadn't told you what I was going to say, because I was still crafting it up until about 2 minutes ago, as any sensible academic should. So key point. The IPCC, in all of their scenarios, the sort of integrated assessment models, suggest the world is going to move to somewhere between 90 and 100% nuclear and renewable for its generation. Closer to home, in the UK, we believe, if we believe the Committee on Climate Change, that we're going to go to about 80% just wind and solar, the relatively uncontrollable and difficult to integrate stuff. So we are moving very, very rapidly to a very different power system. We all know that. The other thing is, if you were to take, I think it's about 200 or so different studies of high renewable share power systems, they all generally concur you're going to need something to sort it out. And it seems to be an exponential relationship between the amount of storage that you require in your power system and the share of energy met by variable renewables. This is not necessarily a new thing. So the world has an awful lot of pumped hydro, and we built it around the time that we all built lots of inflexible nuclear power. So you have something that cannot flex up and down to meet with load, unless you're French, they're the only people who do that. You build something that can complement it by doing that. So I will do one little piece on how much storage we need. So the other key part of this is we run our energy systems with petawatt-hour scale storage. None of this terawatt-hour stuff. We need thousands of terawatt-hours to run the system the way we do currently. So this is the amount of natural gas in store in both Europe and the US. And you can see it flexes. They take the winter of 2014, the US withdrew 1,000 terawatt-hours from its natural gas store. Of course, the calorific value of natural gas is not the same as the exergetic content of electricity, but this hopefully is enough to motivate you that it is true. If we want to do this, we're going to need huge amounts of storage. What I would show, probably tomorrow, when we've successfully had some wine inside us, is that we have done some similar, but much more limited work to the Royal Society to Rulstone and Smith papers and to what Chris Llewellyn Smith presented earlier, where we're looking at, if you were to scale up the amount of wind and solar, what does it mean in terms of the amount of curtailment, and how does this mismatch between supply and demand reduce if you increase storage? There are some slides on that, but I'm not showing them now. What I instead want to do is, because of this usage of multiple decades of renewables data, which you can see here, there is a critical problem with these studies in that they don't have the corresponding multiple decades of demand data. And I'm very glad that Professor Llewellyn Smith mentioned this in his study, because it's something where I think it would be reasonably easy for us to help out and deliver something there. So we don't yet have a comparable synthetic time series of demand where all aspects are held constant in terms of the size of the economy, the number of people in the economy, the makeup of the economy. The only thing that's allowed to vary is the weather. So this is UK half-hourly electricity demand going back over 30 years. And it actually looks very, very consistent. It was growing slightly and then falling slightly. But if you dig into the details, these are the diurnal profiles, so the average profile across the day for the period 91 to 92. I've taken 2 years just so that we can smooth out the effects of a winter being particularly cold or particularly warm. And the 4 curves you have here are for the 4 seasons. Now, let's play a game of spot the difference and see how different are the 1990s ones to the 2020 ones. So again, 2 years. You can see there's been a big change in the evening. Summer evenings, demand used to fall down very rapidly, and now it doesn't. And there's also been a change around the evening peak. So in spring, it's generally quite sunny compared to how warm it is. And in autumn, it's quite dark and dingy. Back then, we were all using incandescent light bulbs, which are very high energy. And now a lot of us have moved to LEDs or low energy bulbs. So you can see that this evening peak has diminished quite substantially. The other key one I'd say is night storage heaters. We used to have quite a large amount of electricity storage in the form of heating up a tank of water in your house overnight to then use later on. But everyone now lives in a shoebox, so there's no space for a large water heater. And so this nighttime peak almost has thoroughly diminished and gone away. You can see the 2 decades in between, you can see these trends have evolved. And I think for a study like the one that we saw earlier, and possibly for the wider community here to study a whole bunch of other stuff, it could be useful to have a consistent, say, 37-year time series of demand with the kind of properties that we are seeing today, with today's technology mix, population, etc. And what we have is something I've been working on for the past couple of years, is an extension to Renewables Ninja, which is creatively titled the Demand Ninja, where we can simulate what electricity or gas demand would look like for multiple weather years. So it starts by taking in, as you would expect, temperature as the key variable that one needs for predicting demand. But we also compound this with solar irradiance, because the brighter it is outside, the more surface heating you have in a building, with wind speed, because that's key in on the wind chill factor that you experience, especially in the UK, as our buildings are very leaky with single glazed windows and the like. And also humidity, because that influences the amount of discomfort that you feel personally. We lag the temperature over time because there's a thermal smoothing effect inside buildings. And then we take the population weighted average across the whole UK to go from what on the top is the yellow line, which is raw temperature, to the black line, which we've given the name BATE because we're not very good at creating acronyms. That's the building adjusted internal temperature. You can then convert from that to heating and cooling degree days, which is a measure of how much heat or how much cool you require. And then that combined with a couple of parameters on how much extra energy do we consume when it is cold or when it is hot, then get you to a synthetic simulation of demand. So the green line that you can just see on the bottom, that is the result of 6 parameters going into a model. The temperature at which you heat and cool, how much energy you need per degree it gets hotter or colder, and a couple of parameters about how you play around with the weather. And that matches quite nicely electricity demand in the country, with the exception of a couple of bits I've stripped out, which are Christmas holidays, because we don't behave rationally around Christmas. So you can see, for example, the beast from the east, March of 2018, exceptionally cold, very high heating degree days, very high electricity demand. And you could see also the summer of 2019, when it's exceptionally hot, you get a small spike in cooling degree days in the UK, and that actually registers as an increase in demand. If we had upgraded this, and I've done the same for 2022, you could imagine the day in which we hit 40.6 degrees around these parts of the country would also register quite a need for cooling. So what I think that might allow us to do, for example, is you could take, rather than historic electricity demand, which is represented here, so this is the demand averaged across each of the seasons, rather than this being quite a variable thing that is changing both based on the weather, so the sort of the sporadic up and down is a cold winter, a warm winter, that we want to keep because that is something we expect in the future. Whereas look at the demand in the summer, the bottom panel here, that's very smooth. The key things are 2005 was around the time when changes to the macroeconomy, the industrialization, increases in energy efficiency started to outweigh other sources of growth, and things like 2009, the great, the global financial crisis, causing a big recession, dropping demand. So you want to be able to strip out these components, maintain these components, and then you also want to be able to play games with the future. What would happen if 80% of homes are heated electrically? What would happen if electric vehicles are very commonplace? Because electric vehicle demand also scales quite strongly with temperature because of the need to heat the cabin up. And that heating is actually quite energy intensive compared to the driving because the electric motors are so efficient. So you could start to change those 6 parameters that you put into the model, and you could start to get very different future demand. So that's something that I'd quite like to talk with various people here to see if it is something we can do usefully. The one other thing I was going to look at, skipping electric vehicles, is to just talk about the economic side of things, because that's what I was originally built to talk about. So what does society want? Terawatt hours of storage, interseasonal. What are investors willing to offer? Possibly something quite different. So I've put this as a Lonely Hearts magazine. We're trying to connect these 2 groups together. So we want tens of thousands of gigawatt hours of storage. Investors are only going to put money into individual incremental projects. They're not going to commit to some grand scale vision. They have capital discipline. They're only going to put money into something they know is going to work. We want extremely long durations of storage to be able to shift energy between the seasons. But that implies you may only be using it once a year, maybe even less than that if you're having to build in multi-year backup for these extreme events. But it's only projects with very high utilization that can actually be profitable. We also want the usage is going to be very dependent on what the weather is like in a specific year, but investors like projects that have a predictable and bankable rate of return, managed uncertainty. And if that uncertainty is one of the key drivers of you making money, it's going to be very difficult for them to raise money. I think all of this suggests trying to rely on purely market prices and market processes is not going to be the way to deliver what we want here. And there needs to be an infrastructure market. For every gigawatt of wind, we want you to put away this much money to put in a gigawatt of storage or something similar. And just a couple of slides to evidence this. Here we have simulated, or rather just done a simple optimization. How much money could a storage device, lithium-ion batteries with 4 hours duration, or sorry, multiple hours duration, how much could they make through arbitrage if they had perfect foresight? So it is simply a case of matching time periods together to figure out maximal profit. We've done that for various markets, so most European countries, Japan, Australian states, and all the US power markets. And done that for different technical configurations, so different durations of storage. So you can see, as you get longer duration storage, your profits go up, which makes sense because you can shift energy further around in time and exploit bigger price differentials. But the marginal increase in your profit, the chart on the right, goes down dramatically as that duration increases. So if you go from 1 hour up to 2 hours, you could expect in Asia you're going to earn an extra $15 to $20 per kilowatt of capacity each year. If you go from 32 to 64 hours, you might earn a few cents extra. And this is a log-log relationship. So you could imagine as you go up to 1,000 hours of duration, the marginal extra value you're going to get is nothing. So, and if your hydrogen caverns are free in terms of their energy quantity, you know, pumping more hydrogen down underground doesn't cost you anything extra. The size of the cavern was defined geologically. You're not paying to fill it in or to construct it. Maybe it will work. But if you have any kind of cost associated with the amount of energy you're storing, not just the power pushing it in and sucking it back out, there will be a problem. The one other thing is the issue of cannibalism. So the more you install, the less money it makes. This is an issue for wind farms and solar farms. You know, Germany, you're seeing at times when the sun's shining strongly, power prices are negative. You're effectively creating a waste product by creating electricity. We've seen this. This is an example for Germany frequency response. So it's seen, observed very much in practice. As with the bars, the volume of battery storage providing that service increases. The line you can see is collapsing. The value of that service halved in the space of 4 years. So the poor folk who built a battery in, say, in 2015, expecting 3,000 euros per megawatt per week, 3 years in, they're only receiving half that because competition has crowded in and is reducing their value. We can see this with arbitrage in the UK. So again, simulation, modeling the UK's power system with more and more storage. So this is the diurnal profile of power prices with the system as it was. As you throw in 5 gigawatts, 10 gigawatts of lithium ion, those peak prices come down quite substantially. And then you can see your utilization of the storage falls as you put more of it in. The profit of the overall fleet of storage peaks somewhere and then actually starts to decline dramatically. So it's less and less worthwhile for investors. And so you could, if you're the first person to install storage, you might be expecting £60 per kilowatt per year. Once you've installed 5 gigawatts, you expect half of that. Once you've installed 10, your profits are now 1/6 of what they were for the first. Very, very quickly, there are various ways around it. One thing I think could be of interest to the mathematical community is how on earth do you model in a sensible way revenue stacking? The idea that you could be bidding into multiple markets, delivering multiple products, because you can do this simultaneously at the top, give half of your power to one service, half to another. You could be doing this sequentially. So sometimes you do one thing, and sometimes you do another. You could be doing this simultaneously with both services getting full capacity. I have a 100 megawatt store. I give 100 megawatts of it to one thing and 100 to another, and just play the game of hoping I'm not needed for both simultaneously. You could also potentially do sequential stacking and be paid for your discharge as well as your charge. So you could be making money from 3 services at 3 different times. For example, you sell frequency services whilst charging up, and then you sell energy in the balancing market or in another system. So finally, I'd say this was the kind of analysis that I was going to show, but perhaps if I talk tomorrow on that topic more coherently, you'll see. But there's a website, you possibly guessed, with Renewables Ninja and Demand Ninja. There's a theme developing here. I name things stupid names. We also have the Energy Storage Ninja, which is a website that allows you to do some of these calculations yourself. So it's interactive. You can play around with the storage quantities or efficiencies, which country you're considering, to start to do these kind of calculations on what the scale of the system might be. You can look at how much money it might be able to make from arbitrage and a variety of other things. And also, most of these slides have come from a book, Monetizing Energy Storage, which will be published later on this year, hopefully by about June. Sadly, by Oxford Uni, we tried getting published here, but they go to us for a while. So we had to go with a competitive universe. So my finishing slide was just to throw up a few questions. What might be of interest from my perspective? So firstly, would conjoint time series of renewables output and demand be useful? And would it be useful to perhaps make static time series, as in considering a particular point forecast for the amount of electric vehicles, amount of electric heating and so on? Or would a dynamic approach be useful where you could play with a bunch of sliders and say, we need this much electric heating and this is the size of the population or whatever. So you can play with those various components to create your own demand scenarios. I didn't speak about electric vehicles, but could do tomorrow. Basically, they're very complicated, and that's going to be an interesting topic to look at. I think within about 5 years, there may be 150 gigawatt hours of electric storage in cars, which could be utilized by the power system. So it's going to be complicated because it's not 10 neatly defined, static units that can be controlled through the existing balancing mechanism. It's going to be 5 million vehicles. On modeling the value, questions about how on earth you do this dispatch. To me, it sounds like an incredibly complicated optimization puzzle, but to you, it may not. And on flexibility, just more generally, storage is by far not the only thing that can do this. It can arbitrage over time, but then you have interconnectors which could arbitrage over space. Some, I think, quite rightly say we shouldn't be relying on that, especially in times of great need. When it was incredibly cold earlier on back in December, we were exporting to France at a time when electricity demand was at its highest and wind was low, because France had even bigger problems than we did. There's also demand side response. Octopus are now running trials where you can get paid quite handsomely for shutting things off. How do you model the interaction between all these different forms of arbitrage to work out, is there even a market for these kind of huge amounts of storage to be expected? How do you schedule all of these things simultaneously? I'll leave that there, but that is finished. Iain, thank you very much.
Thank you. Lots of interesting questions. I think the only thing to do is to have a bit further discussion for those who are around tomorrow.
Yeah.
One way or other. There's just so many questions that this is throwing up that we would like to talk a bit backwards and forwards about them. Have some more time for discussion.
But I don't. That's the purpose of having a whole week or 2 weeks.
Yes,
here.
exactly.
Good.
But to all three speakers, to Chris for coming in remotely, which is always more challenging, to Tom and to the ESO view, which is rather important, and to Iain, without whose data all the rest of us would be completely stuck. We say thank you very much, and we'll take this further. Thank you now. And there's, I understand, some wine around.
Very crucially there.